MATU 206, Week 2. Place value is very important for students to understand, and it assigns a value to a digit depending on its placement in a numeral. We have a decimal point here, and to the left of it we call it the units, and where we recognize it as ones. It's really 10 to the 0 place, and any value raised to the 0 power is equal to 1. And so in this case we have 8 times 10 to the 0, 8 times 10 to the 0, which is 8 times 1, so we have 8. Here we have 7 in the tens place, which is 10 to the 1, so we have 7 times 10 to the first, which makes 70. Here we have 6 in the hundreds place, which is 10 squared, so we have 6 times 10 squared, or 100, which makes 600. And to the left, going further, we have a 5 in the thousands place, so we have 5 times 10 to the third. 10 to the third is 1,000, so we have 5,000, and we typically will add these and call it 5,678. We do have our decimal point. Going to the right, we do have the tenths and hundredths, and the tenths really is 10 to the negative 1. So instead of multiplying by 10, we're dividing by 10. That's tenths. The hundredths place is 10 to the negative 2. Notice this way we're adding exponents, and going this way we're subtracting exponents. And that is 1 divided by 10 squared, or 1/100th, and it keeps going to the right that direction. The Egyptian numeration system consists of these symbols: a vertical staff, which is our equivalent of 1, the heel bone 10, the scroll is in the hundreds, the lotus flowers in the thousands, pointing finger 10,000, pollywog 100,000, astonished man 1,000,000. So if we're going to do this and translate this number, we can start either direction. If we start with the 3, we need 3 would be 3 of these vertical staffs. The 2 in the tens place then is we need 2 of these heel bones. The 1 in the hundreds place means we need 1 of these scrolls. The 5 in the thousands place means we need 5 of these lotus flowers. 1, 2, 3, 4, 5. The 4 in the 10,000s place means we need 4 of these pointing fingers. 1, 2, 3, 4. The 3 in the 100,000s place means we need 3 of those polywogs. 1, 2, 3. And the 2 in the millions place means we need 2 of these astonished men. If we were going to write a number, let's say like 348, well, we have an 8 in the ones place, means we need 8 of those. 1, 2, 3, 4, 5, 6, 7, 8 vertical staffs. We have 4 in the tens place, which means we need 1, 2, 3, 4 of those heel bones. And 3 in the hundreds place means we need 1, 2, 3 of those scrolls. The Babylonian numeral system really only has a triangular mark that indicates 1 and an eyeball type mark. I've seen them sometimes written with an eyeball there, meaning 10. In order to represent this, the 0, of course, is 0, but the way we have to translate this, because we have base 10, they have base 60, so we're worried about our ones place, our 60 to the first, our 60 to the second, our 60 to the third. Now 60 to the third power is 216,000. 60 squared is 3,600. 60 to the first is just 60, and then we have our ones, which are just ones. So if we have a number of 305,470, first thing I'm going to see is that this digit is bigger than 60 to the third, And so I'm going to see, it appears that there is one of these 60 to the thirds in there, so I can take away 216,000. And that's where I get this mark here. That stands for 1 60 to the third, or 216 thousandths. Then I look at 60 squared of 3600. How many 3600s will go into 89,470? So I do 89,470, and I have to divide by 3600. I can shortcut it by taking the zeros off. 360 goes in 2 times, which is 720, and the difference is 4 and 7 and 2, and I can bring down the 7. And 360 goes into there, I believe, 4 times, so 360 times 4 is 24, carry the 2, 12, 14, 40. So I can find the difference left over is 7, 0, 307, and that's where I get 2 of those for 20 and 4 of those for 4, 24. And I have to subtract to find out what's left, so I have 3,600 times 24, because that's how many times 3,600 went in. So I have 0, 0, 24, carry the 2, 12, 14, 0, 0, 12, 6, 7, 0, 0, 4, 6, 8. So then I subtract 86,400 from here to find out how many is left. 0, 7, 0, 3. And I don't agree with this number here, but okay. So I want to see how many times, so 60 squared won't go in there anymore, so I want to see how many times 60 will fit into there. So I have 3070 divided by 60. Now, of course, I can throw away the end zeros again, so 60 goes into 30 5 times, which is 30, and it goes in 1 time, which this 5 is 5 tens, where I get these 5, and this 1 is just the 1 1, where I get that 1. But then I have to do 51 times 60 to find out how much I subtract. 0, 6, 0, and 3. So 3060 is 10. And so, yes, that's wrong. That should be a 7. And the 10 left over then is just 10 of these, or makes one of those things for 10. It is vertical from least to greatest. And what they do is they have their ones place, and then they have what's their 20th place. But then they get strange, and instead of doing 20 squared, it's 18 times 20. And I read about some reason once upon a time why they thought they did this. It used to not be, but they changed it at some point. And then we have 18 times 20 squared, and 18 times 20 cubed. And 20 squared is 20 times 20, or 400. So that means 18 times 400. 400 times 18 makes 0, 0, 32, 0, 0, 4, 0, 0, 2, 7. So that's 7,200. And then 18 times 20 cubed, we would then do a 7,200 times 20. So that's 0, 0, 0, 0, and 0, 0, 4, and 14. So that's 144,000, and the 18 times 20 is simply 16, 0. Wait a minute, what am I doing? 8 times 0 is 0, 8 times 2 is 16. Now that's, I miswrote it. And then 0 and 2, so we have 360. And so when we have 305,470, we're trying to find out how many of these will fit in, and I believe that there are two of them, so 144,000 times 2 makes 0.00882. So I subtract 288,000. So I have to put two dots at this level, and then 0.74. That's a 2. That's a 9, 15, 7, 1. So that's 17,470 left over. And how many of these 7200s will go in there? It looks like two of them, so 7200 times 2, 0, 0, 4, 14. It looks like 14,400, 0703. And so I have to put two of those. And how many 360s will go in there? Let's see here. 3, 6, 9, 3, maybe about 9 of them. So 360 times 9 is 0, 54, 27, 8, 9, 31, 30. No, not 9. Must be 360 times 8 is 0, 48. Carry the force. 24, 32. Nope, not 8 of them. Must be 7. 360 times 7 is 0, 42, 21, 25. So there'll be 7 of these. So I draw a line for 5 and I put two dots above it in this place. And that's 25, 20, and 0, and 5, and it's got to be 8 then. Where did I go wrong? 8 is 0, 48. Okay, I'm trying to squeeze my work in too tight. 360 times 8, 0, 48, 8, 16, 4, 32, 36. No, it won't. 7 is 0, 42, carry the force, and 21, 25. Oh, that's 2 to make 10. 0, 5, and 5. Should be another 360 in there. 0, 4, 9, and 1. So we have to put another dot there. But then we find out how many 20s go into 190. And that's about 8. So we have 5, 6, 7, 8 there. And that was 9 because then that's 180. And we have 10. So then we have 2 lines down there. And that's how I would do this. In my head, scratching around, this may be more correct, but that's the process. I don't know. There's things that I don't agree with on this example that came with the book. You can look at what I did and what they did and decide which one's correct and let me know. The Roman numeral system has an I, which is 1, a V is 5, an X is 10, an L is 50, a C is 100, D is 500, M is 10,000. We call it a subtractive system because if you put the I in front of the V, you end up with 5 minus 1 for 4, or an I in front of the X, you end up with 9. It's inappropriate to put the I in front of anything larger than an X. The X in front of the L is 40. The X in front of the C is 90. It's inappropriate to put the X in front of anything other than the L or the C. And 400 can be made by putting the C in front of the D or C in front of the M. And somewhere along the line, they decided they needed bigger numbers. So if you put like a bar over the X, it's 10,000, and or a bar over the V, it's 5,000. So if we're going to work with 15,478, what I'm going to start out with is I see that there is a 10,000 in it, so I have to put the bar, and then I have to find out, well, what's left is 5,478, and so then I need a 5,000, and I can take away the 5,000 to see what's left, and I see I have 400, and so 400 is C in front of the D, and I can take away 400 to see what's left, and I have 78 to make 70. I can use the 50 and 2 10s, so L and X, 50 plus 10 plus 10, and there's 70, and then I have to make an 8, which is the V, take away the 5, and I have 3 ones left, and so that's how we come up with that. Other number base systems. We are so used to the decimal system, which is base 10. And what that means is as we're counting or adding, when we hit 9, we carry 1 to the next group. So base 10, we carry at 10. And if we're going to borrow, we borrow, and when we're subtracting, we borrow a group of 10. Well, in the base 5 system, what happens is we carry at 5. So if I go 0, 1, 2, 3, 4, I only have these 5 digits in base 5, so I can't write anything down. So what I have to do is I have to carry, and now I have 1 in the groups of 5, and so that would be decimal, our base 5, and this is, we would say 6. 12, 1, 2, 1, 3, 1, 4. But again, I don't have a 5, so I have to carry. And 2, 1, 2, 2, 2, 3, 2, 4, carry. So base 5 says I only have 5 digits to write, 0 through 4. And I carry when I get to, when I'm going to go past 4. And I borrow groups of 5, which we would have to write as 1, 0 here. If we're going to convert, and so what we have is our place value. What we have is place value. So we remember the decimal point we talked about. In this place, in the decimal system, we call it the ones. It's really the 5 to the 0 place. This place is the 5 to the 1 place. This place is the 5 squared place. This is the 5 cubed place, and so forth on to the right. And on to the left, it'd be 1 over 5 to the first, 1 over 5 squared, 1 over 5 cubed, that way. And so if we're going to convert 1, 1, 2, 4, 4, 5, we have a 4 there, a 4 there, a 2 there, a 1 there, and a 1 there. And so what we can do is see that we have 4 times, well, 5 to the 0 is 0, so that's 4. We have 5 to the first, well, that makes 4 times 5 in our decimal is 20. In decimal, 5 squared is 25, so we have 2 times 25, or 50. In decimal, 5 cubed is 125, so we have 125 plus 50, and here we'd have 625 decimal, and so we'd have 625 plus that, and when we add all that up together, we get our base 10 value of 824. Now the binary system is only 2 digits, and this is important because it's how computers work. It's either on or it's off. There's either a value there, a charge there, or there is nothing there. And so that's how computers work. They're really fast at binary math. So to convert this, now in binary, remember we have our decimal. This place would be 2 to the 0. This place is 2 to the first power. Then we have 2 squared, 2 cubed, 2 to the fourth power. Or in base 10, we have our 1's place, our 2's place, our 4's place, our 8's place, and our 16's place. So to convert 10112 or 111 in base 2, we have a 1 there, a 1 there, a 1 there, and a 0 there, and a 1 there. So what we end up with is 1 times 1 is 1, 1 times 2 is 2, 1 times 4 is 4, 0 times 8 is 0, so we don't put anything there, and 1 times 16 is 16, So we get 16 plus 4 is 10, or 20 rather, 22, 23 is how we get our base 10 value of 23 is what that is in base 2. Now to go back to base 2, what we do is more of that subtraction stuff. So if we're going to convert 27, what I need to know is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth power. That's 1, that's 2, that's 4, 8, 16, and 32. Well, I see that there are no 32s in there, but there is a 16 there that I have to subtract, so that's 1, 1. And so I have in the 2 to the 4's place, I have a 1. And I see that I have 11 over. Well, 16 won't go into it, but 8 will. 8 will go in one time, and then I subtract that 8, and I have a 3. And then I'm looking at 2 squared. Well, 4 won't go in, so that's why I have a 0 there. 2 will go in one time, which is why I have a 1 there, and I have a 1 left over, and then 2 to the first goes one time. And so that's how I change 27 in base 10 to 11011 in base 2. Base 12, this one's fun because then you get to use the T and the E because you have 12 digits. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And because we carry at 12, we need this digit to represent the 10, what we would call 10 in base 10, and that digit to represent the 11 in base 12. And then we would carry. So we in base 12, we carry when we get to just past E, and we borrow groups of what we would call 12. If we're going to convert this, we have this, which is 12 to the 0, this is which is 12 to the first, and this which is 12 squared. So here we have our 1's place, our 12's place, and our 144's place. We'll call it in base 10. We put a T, a 2, and an E. So T is 10, so we have 10 times 1, or 10 that we're adding. Here is 2 times 12, 2 times 12, which is 24 that we're adding. And here is the E, which 10, 11. So we have 11 times 144, which is 1584. That when we add all these together, we get the 1618. To go the other direction, I need to know that 12 to the 0, 12 to the first, 12 squared, 12 cubed. I need to know all these values. So 12 is my 1's. This is my 12's place. This is my 144's, and whatever 144 times 12 is. 8, 8, 2, 4, 4, 1, 8, 2 carries 7. So this would be my 1728's place. And I'm looking then at did I do that right? 2 times 4 is 8, 8 and 2, 4, 4 and 1, 8. Oh, I missed a place, didn't I? 12, 4, 5, 6, 1, 2, 3, 4. No, I have 4 digits here. 7 and 1, so that's 1728. And so if I have 1277, I see that there is no 1788 in it, but I see that 144 will fit in. And looking over here, I see that it goes 8 times, so 144 times 8 makes 32. 32 plus 2 is 34, 8, 9, 10, 11. So it will go 8 times 32, oh, 35, yes. And I can subtract out 1152 from here. So that's 5, 2, and 1. There are no more 125s, but 12 will go in there. Looks like 12 will go in 10 times, so I get to use this T, and 10 times 12 is 120, which leaves 5. and so 12 to the 0 is 5. So 1,277 in base 10 equals 8t5 in base 12. Now we get to talk about sets. A set is any group or collection of objects. So we frequently write about sets in these curly brackets. So 2, 3, and 4 is a set. It has 3 elements in it. 3 elements. 1 element, 2 elements, 3 elements. And a method of denoting is to list the elements inside these braces, curly brackets, whichever. Each element is listed only once, so it would be inappropriate to say 2, 2, 2, 3, 4, because in a set we don't need to duplicate the items. The order of the elements is unimportant, although typically mathematicians write them in order from least to greatest. We symbolize that an element belongs to a set by using this symbol. So 4 is an element of 2, 3, and 4. Whoops. And a set must be well defined. We must be able to tell whether or not an object belongs to a set. If we can't, then it's not well defined. Set builder notation is just a funky way of writing sets, where this is the set name. Doesn't have to be E. It could be S or Q or T or whatever. And then this here says of all elements X. And this bar here says such that. And then you can describe the set here at this point. You can either list the set or describe it, such as X is an element of natural numbers and X is less than 11. So you can describe the set or you can list the elements at that point. So write the set A of all elements 2k plus 1, k being equal to 3, 4, and 5 by listing its elements. So we can make a table. We have 3, 4, and 5, the values of k. We plug them into 2k plus 1 to get the set 7, 9, and 11. Two sets are equal if and only if they contain the same elements. So 2, 3, and 4 is equal to 3, 4, and 2 because they both have a 2, they both have a 3, they both have a 4, and that's all they have. They have exactly the same elements. There is a one-to-one correspondence if they have the same number of elements, not necessarily being the same elements. So we have a set 1, 2, and 3, and a set with the elements A, B, and C can be set up in a one-to-one correspondence. And they can go in any order, any pairings, so we can have multiple different arrangements. But they will be a one-to-one correspondence does come up. The fundamental counting principle, not exactly sure why it slides in at this point, but this is where it happens. If an event M can occur in M ways, and after it's occurred, event N can occur in N ways, then the event M followed by the event N can occur in M times N ways. So, for example, you have 3 shirts. You can wear those shirts in any order. You could, if you have shirts A, B, and C, you could wear them A, B, C. You could wear them B, A, C. You could wear them in the order B, C, A. Any order you can wear them. And the order in which you wear your shirts has no bearing on the order in which you wear these 4 pants. So you can combine them in any way. And the fundamental counting principle says that your 3 shirts combined with 4 pants gives you 12 different ways of wearing these, combining these things together. Or if they have, you go to the ice cream place and they have 6 flavors of ice cream and waffle cones, sugar cones, and cake cones, then those flavors of ice cream can go together with those different cones in 18 different ways. So the fundamental counting principle just says each event being separate can happen in that many ways, and you just multiply them. Two sets A and B are equivalent, not equal, but equivalent, written as, yes, there's the little symbol, and I always forget this, that means equivalent, if there exists a one-to-one correspondence between the sets. So A, B, and C, if I can have 1, 2, and 3, I can say that these two sets are equivalent. They aren't equal. It's just that there is a one-to-one correspondence. Um, Equal means they have exactly the same elements. So if we're given these four different sets, determine whether the following statements are true. A is not equivalent to B is true because A has four elements and B has three elements. A is equivalent to C is false because A has four elements and C has three elements. I cannot set up a one-to-one correspondence. B is equivalent to D. Well, B has three elements, D has three elements, so that would be true. In fact, they're the same elements, so not only are they equivalent, they are also equal in this case. Equal means equivalent. Equivalent does not mean equal. So C is not equivalent to D, which is false because they both have three elements, so a one-to-one correspondence could be set up. So A is equal to B, four elements, three elements, none of which are the same. That's false. A is equal to C, four elements, three elements. That's also false because none of which are the same and they have different quantities. B is not equal to D. Well, that's false because actually they both have A, they both have B, and they both have C. They are equal. C is not equal to D is true because even though they are equivalent with the same quantity of items, of elements, they are not equal. They don't have the same things. Now the universal set, that's just all items that are qualified or fit, is of all elements under consideration. We usually denote the universal set with a capital U, and U such that X for all X is a member of the United States Senate. So we're talking about in the United States Senate, is that 104 members, 2 from each state, plus Guam and Puerto Rico or something like that, have 2 each with their non-voting members, I think. Denote the universal set with a large rectangle. So we have a large rectangle here. That's the universe. That's the universal set. And so this, in this case, is representing all of the senators. And now F, this circle in here, are female U.S. senators. There are males, so that they certainly aren't the whole universe. And consider that the members of the universal set who are not females, so F is there, and then all the not females, or in other words, the complement. Notice it's not spelled the same as my "your hair looks nice today" compliment. Is written as this bar over F, so it's a set of all elements in the universal set that are not in F. And so this green shaded area is the U.S. senators that are not female in this case, and so that would be not F, or the complement of F. So if the universal set is A, B, C, D, so we have here this whole thing is A, B, C, D. B is just C and D. Find the complement of B, or not B. Well, not B, out of the universe, we take out C and D, leaves just A and B. Not the universe, that means nothing there. Well, that's the null set. And not the null set means A, B, C, and D, all of them. If the universe is an animal in the zoo, so you think of all the animals in the zoo, and so we have all the animals in the zoo make the universe, and S is, the set of S is the snakes, so they're the snakes, then the complement of S, or not snakes, are all the animals that are not a snake. Set B is a subset of A, so this symbol here is represents subset, or part of the set. Only if and only if every element of B is an element of A. When a set of A is not a subset of another set B, we write A is not a subset of B. So if we had 4, 5, 6, and 7 being our set A, if B has 4, 5, and 6, it is a subset or a part of the set of A, so we would write B is a subset of A. Suppose B is a subset of A and B is not equal to A. So then we have the universe, all items under consideration. We have the set A, and then B is just a part of A, but it's not equal to A. That means there has to be at least one element that is part of A that is not of B. There needs to be at least one thing. We say that B is a proper subset of A. So this is, if this is subset, this is proper subset. Then there means, okay, so it's a proper subset of B there. Given set A with those 5 characters, set B with those 2 values, and P where x is, for all x is 2 to the n minus 1, where n is a natural number, which are sets or subsets of each other. So we see that 2 to the first is minus 1 is 1, 2 squared minus 1 is 3, 2 cubed minus 1 is 7, and so forth. And we see that so P is 1, 3, 7, 15, etc. B being 1 and 3 is part of P, so B is a subset of P. Is A a subset of P? No, it's not, because A has 2 and P does not. But we can also be that B is a subset of A, and B, yes, I was looking at P. B being 1 and 3 is a subset of A. A is a subset of A, B is a subset of B, and P is a subset. So these sets are all subsets of themselves in addition. Given that A is these 5 digits and B are these 2 digits, and P is x equals 2n minus 1, where n is a natural set of the natural numbers, which sets are proper subsets of each other? Well, B is a proper subset of A because it's completely there, and B is a proper subset of P, but these other things where they're subsets of themselves don't make a proper subset, because proper subsets have to be at least one element not part of it. Is the difference between a proper subset and a subset. Let's see here. So again, if A consists of 1, 2, 3, 4, and 5, and B consists of 1, 2, and 3, A can be a subset of itself, B is a subset of A, but A is not a proper subset of itself, because it has to, in order to be a proper subset, there have to be some values or elements that are not part of this set. And since B does not have 4 or 5 in it, it is a proper subset of A. Suppose A and B are finite sets, meaning they don't go on forever. They have a limit to their size. Now, if A equals B, that means they are the exact same set and contain the same elements, then the number of elements in both A and B are also the same. A and B are equivalent, also because they're equal, and it's possible to establish a one-to-one correspondence because they have the same number of elements in the set. If A is a proper subset of B, then the number of elements in A has to be less than the number of elements in B, because remember, to be a proper subset, it needs fewer, or needs at least, there needs to be at least one element in B that is not in A. And it's not able to establish a one-to-one correspondence because the number of elements are not the same. Now, those are finite. If they're infinite, then they are elements or proper subsets of each other. And it is possible to establish a one-to-one correspondence between the sets because they are infinite. They keep going. Thus, n is equivalent to w. Now, what's all this stuff mean? Consider the following sets. X is a college graduate, so this set. So C is the set of all college graduates. S is the set of all people who earn at least $40,000. So you're a marketing firm or something like that, and you're looking at a city or an area or a state, and you're trying to market to all college graduates that perhaps that earn $40,000 or more. So you want to be able to identify who these people are. And so if we're talking about the intersection, that means we want only the people who are both college graduates and make $40,000 a year. So we have the universe here. We have everybody in the city. Here we have everybody who's a college graduate. Here we have everybody who makes at least $40,000 a year. But here's the group we're interested in, the intersection, the people who are both college graduates and make $40,000 a year. That's what intersection means. The people or the elements that are in both sets. The elements in both sets are the intersection. So if we have A is equal to 1, 2, 3, 4, and 5, and B is equal to 2 and 4, then the elements that are in both, oh, maybe we can even make it 0, 2, and 4. The elements that are in both sets are 2 and 4. So A intersect B is equal to 2 and 4. Just the items, the elements that are in both sets is what the intersection is. And so its intersection is and. The elements are in A and in B. So if we're going to find intersection of A and B here, I see that there is a 3 in both sets and a 4 in both sets. So the intersection of A and B is 3 and 4. If I look here, 0, 2, 4, 6 looks like the even numbers, 1, 3, 5, 7 look like the odd numbers. There are no elements in common. That means it's the null set, and we can say that they are disjoint. Here I see that A is 2, 2, 4, 4, and it looks like B is all natural numbers, and C is the even numbers. So A intersect B is set A. It's all the even numbers. Because as these continue on going 5, 6, 7, 8, 9, 10, more and more, it will contain all the even numbers. So now we have the same group here where we have X, set C is all the college graduates, and set S is everybody who earns at least 40,000. Suppose we want to mail a questionnaire to just every person in this city. So the universe is this city, and we want to contact all college graduates and everybody making $40,000 or more. This is the union. This is just everything. So if we have set A is equal to 1, 2, 3, 4, and 5, and we have set B is equal to 4, 5, 6, and 7, then I just want everything. I want the union is everything in A, 1, 2, 3, 4, and 5, and everything in B, but I do not have to rewrite 4 and 5 because they only have to be listed once. So that is the A union B is just everything there. So the union of two sets, the key word is or. If it's in set A or in set B, you take it. So here we have 1, 2, 3, 4. Here we have 3, 4, 5, 6. And so we're going to have 1, 2, 3. Don't need that 3. 4. Don't need that 4. 5 and 6. A union B, 2, 0, 2, 4, 6, 1, 3, 5, 7. We just take everything. So we take the 0, we take the 1, we take the 2, we take the 3, we take the 4, we take the 5, we take the 6, we take the 7, and so forth on up. And A union B, 2, 4, 6. It's really just set B because all of A is contained in B. Now we have these two sets again. Um, the set of individuals earning at least 40,000 but not a college graduate is called the complement of C relative to S, or the set difference of S and C. So earning at least $40,000 but not a college graduate. So we want this, but not that. So that's everybody who is that is complement relative, related to, or C. So that means all elements of B and all elements that are not in A. So it's shown as B minus A, or it's not really minus. It's just that take the set of B and take out all members of A. So here's the relative. So we had all of B, but we took out all the members that are in A. If A is DEF and B is ABCDEF and C is ABC, find all members in A and take out all the ones that are in B. So since D, E, and F are in B, when we take all those D, E, and F out of A, we're left with the null set. B, take out the C, so we take out the D, E, and F, we're left with ABC. If we have B and we take out C, we still have those, so we are left with D, E, and F. And C, take away B, wipes all those out, so we're left with the null set. Properties of set. Commutative property for like addition means you can add in any direction or whatever. So if we have A intersect B, that's the same as B intersect A. If we have A union B, that's the same thing as B union A. So intersection and union is commutative. Associative property says we can group things, and it works. So we can intersect. If we take the A, or if we intersect B and C first and then intersect with the A, we'll get the same value as if we intersect A and B first and then intersect with set C. If we find the union of B and C and then union with A, we get the same value as if we union A and B. So this is saying the order in which we intersect and the order in which we make a union does not matter. Distributive property. If we have B union A and we're intersecting A, then we can do the intersection of A and B, and we can do the intersection of A and C, and then put those values together. We're distributing this A intersect over the union. So how can we describe these Venn diagrams here? Well, it looks like we had A union B put together, but then we took away the intersection. So that's what this is saying, is A union B, and then you just take away out the elements that are in A and B. Or it's A union B and intersect it with the things that are the complement or not the intersection of A and B. Or you can take all of B out of A and all of B all of A out of B, and then union them together, put them back together, and that's what you get. And this one, we did A intersect B, which is that part, and put it together with B intersect C, which is that part. So we have the union of that part and that part. Here it appears that we had A and we took out everything that was in B, and we took out everything that was in C also. And A, we took out everything that's in both B and C, is what that says. And D, looks like we just put A and C together and then took out the B and put it together with the intersection. Now, using Venn diagrams as a problem-solving tool, this is really not very well. It can be fun, but it can also be a headache. Region A contains all students. So suppose M is a set of all students taking mathematics. So there's all the students taking mathematics, and E is a set of all students taking English. E, identify the students described by each region. So A are the students that are taking math and not taking English. C are the students taking English and not taking math, and B are the students taking both math and English. And I always forget this D out here, the rest of the universe, are all the students that are not taking math or English. So watch out for that part. And this is huge. In a survey of 110 college freshmen that investigated their high school backgrounds, the following information was gathered. So we get all of this information about these 110 freshmen. How many students took biology, but neither physics nor mathematics? So out of 110, our universe is 110 students. So we have 25 of them took physics. We have 48 of them took mathematics. But then we have this overlap here of 10 took physics and mathematics. So I guess I better erase that and draw it better. So it looks like I have physics, mathematics. I'm not drawing my picture very well, am I? Should just go with the ones that are already drawn. So I have my big circle here, I have my big circle there, and I have my big circle there. And if this is physics, math, and biology, what it looks like is 5 took all 3 subjects, and so that little piece right in there is 5. And you always got to start with the centerpiece. 5. And then 6 took physics and biology, but 5 of them are already here, so that means there should only be interesting. They're putting that is 5 took all 3 subjects. Oh, that's because they're backwards. Yes, this one that I just wrote is here because I wrote physics and mathematics and biology. I have these 2 circles. Those 2 circles are swapped compared to down here. And 8 took biology and mathematics. So biology and mathematics, 8 is here, but I already have 5 that are in both of them, so that would leave a 3. And 10 took physics and mathematics. 10, but I already have a 5 in the center, so that would leave 5 there. And now I have 48 took mathematics, but I already have 5, 5, and 3 makes 13. And so my mathematics ends up being 48 minus this 13, or 35. 25 took physics, but I already have 5, 5, and 1 that took physics. So that's 11, so that means I should have a 14 there. And 45 took biology, but I already have 5 that took everything, 3 that took math, and 1 that took physics. So that's 9, and 45 minus 9 makes 36. And that's how we come up with this group. But if there are 110, if we add all those together, we find out that there were 11 that took nothing, took none of them. So how many students took biology but neither physics nor mathematics? Then you can start looking at all these this explanation, but you can look at biology. They took it, but they didn't take math and or physics. So there was 36, and you can start looking at. Go ahead and read through all this stuff down here. But that's the way it's set up. And then you need to just how many took physics, biology, or mathematics. Well, then you're adding things because of the or. And how many did not take any of the 3 subjects? Oh, I guess I already gave that away by saying 11. Cartesian products. One way to produce a set from 2 sets is by forming pairs of elements of one set with elements of another set. So if we have a set P is blue, green, and white, and that's pairs of pants, and shirts is blue and red, we can put our shirts on one side, red and blue. We can put our pants on the other side, blue, white, and green, and then we can form the sets. So we have blue and red, we have blue and blue, we have white and red, white and blue. So a 3 by 2 Cartesian products, 3 by 2, is going to give us 6 ordered pairs. And equality for ordered pairs, if and only if the first components are equal and the second components are equal. And so they both sets of components have to be equal for the to be in equal ordered pairs. Um, and ordered pairs are if every element of A is also an element of B. So if A, B, and C, A cross B, we have A with 1, A with 2, A with 3, B with 1, B with 2, B with 3, C with 1, C with 2, C with 3. B cross A, we would then go backwards and say 1 is with A, 1 is with B, 1 is with C. So this would be more of our X value and this is our Y value. That's so order kind of matters here. And then A cross A, we're going to have AA, AB, AC, BA, BB, BC, CA, CB, CC. So we would have um, the Cartesian product is going to look like A, B, and C, A, B, and C. So you have AA, A, B, A, C, B, A, B, 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 C, C, A, C, B, C, C is how we get that.